Hey gang, welcome to another Worksheet Solutions walkthrough for Stereoisomers and more RNS practice. You know the drill. You've seen a video, you attempted the worksheet, maybe looked at the answers and you were looking for a deeper explanation. Well, you're in the right place because we're going over this worksheet. We're going to do it problem by problem. We're going to see how each one is done, and hopefully you'll get the answers you were looking for. In problem one, we see something that I've personally seen on exams over the years. Very often you just get a giant structure and no indication of where stereocenters are. You have to, one, identify where the stereocenters are, two, make sure they're actually chiral, and three, assign RNS appropriately. So if we take a look here, what I want to do first is just identify where these stereocenters are. I'll just put a little asterisk by them. So I see one. So remember, we need to be attached to at least 4 different things, right? So I see one right here. I see one right here. See one up here. This kind of looks like one, but it's faking, right? It's a front for a stereocenter because these are two CH3s, not a stereocenter. This is a stereocenter. This is a stereocenter. And that pretty much does it, okay? So if we take a look here, let me fill in my lowest priority group. Oh, nope, there are no such thing as two wedges on the same position, right? So we have a hydrogen. The lowest priority group is facing away from us. We can just assign RNS and take it. So you can see that this carbon right here is attached to 2 carbons and has a hydrogen. This carbon down here has 2 bonds to oxygen, so you count oxygen twice, and then another oxygen. So you can see that clearly this is beating out this, and then this carbon up here has 1 carbon and 2 hydrogens. So I think you can see that the priority goes 1, 2, and 3. So we look like and will be R. Okay? So that's the first one. That one was a bit tricky with the double bond with the oxygen. Then if we look up here, you'll see that we have a hydrogen that is implied facing towards us, so we can assign stereochemistry and take the opposite. So now we need to do kind of some, I'm going to erase this asterisk as well. So I think you'll see that the CH3 is going to come in third. Nothing interesting really going on with it. However, we have a tie here because there's a CH2, right? CH2. And then we get to this position where we have this carbon's attached to a carbon, and a hydrogen. This carbon, right, if I draw this out, this up here is oxygen, carbon, hydrogen. This carbon down here is carbon, carbon, hydrogen. So this up here is 2, this down here is 3. So then if we assign stereochemistry, this was supposed to be 1, and this is 2, sorry. Our wheel is going like this to the left, but we have the opposite because our lowest priority group is facing towards us, so we look R, okay? So now moving along, we've handled these two, well, here, I'll leave the asterisk. We've handled this stereocenter, so let me erase this, erase that. So up here, our lowest priority group, the hydrogen, is facing away from us. Oxygen obviously takes first. Now we have a couple things going on. I think you'll see though, there's a tie here, and then if we move here, this is just a plain old CH2. This has a lot more going on. So this gets the second, this gets the third. Lowest priority group is facing away from us. We're turning to the left, so this is S. Okay? Just double check myself to make sure I'm doing it properly. So then over here, now we have some interesting things going on. So this carbon right here, right? So we have a CH2, so this carbon right here is attached to carbon, hydrogen, hydrogen. This carbon over here is attached to nitrogen, carbon, hydrogen, and this carbon up here, because there's a double bond, is attached to carbon, carbon, carbon. However, even though this is a double bond, this carbon is attached to a nitrogen. So this position comes out first, this then comes in second, this comes in third. Lowest priority group is facing away from us, so we can assign as is. We're going this way in the direction of 1, 2, 3. We are S. Okay? And last but not least, me erase these numbers. We have our lowest priority group facing us. The nitrogen comes in first because it's heavier than carbon, right? Periodic table says so. That's the first period, or that's the period they're all in. So first, and then we get in second over here just because we have more carbons. This is just a plain CH2. That's 3. We look R, but we're actually S because lowest priority group is facing towards us. Okay, if you are having some issues sorting that out, maybe watch this again. Just really take your time and make sure you actually draw these out to show like priority and whatnot and where the ties are broken. But on to problem 2. Okay, gang, so in problem 2, I'm just gonna throw up the structures with the stereochemistry label with some other things, you know, like indicated, just so you can pause the video if you need to kind of see what was assigned, how it was assigned. But I'm speaking to more about the stereochemical relationships between these molecules, and I want to make sure this, you know, this segment of the video doesn't last forever. So if we take a look here, we are attached to 4 different things. We've assigned the stereo, stereo configuration here. So we have one stereocenter, and here it's S, and over here it's R. So this is a mirror image, right? So if everything, there's only one stereocenter here, but hypothetically, if there was, you know, configuration at multiple stereocenters, and then over here we had the opposite of everything, that would be the mirror image, the left and right hand pairing. These two, because they are exactly opposite in stereochemistry, exactly opposite, that makes them enantiomers. So remember, right, you can't just have one thing be an enantiomer. It's a pair, right? It's a relationship between 2 stereoisomers. So the relationship between these is that they are completely opposite. So this is your left and right hand. They are opposite in every way. They are a mirror image of each other, but they are non-superimposable. You could not put one on top of the other. So this is the first of 5, so let's move on to the second. Okay, gang, so in the second problem, in problem 2, you can see we've S and S configuration in this one structure, and then we have R and S. So one thing I want to highlight, I hope you can see I didn't label anything over here because the stereocenter, nothing changed about it from this structure to this structure. So if nothing changed, it's the same configuration. And I hope you see that while I did label everything here, all that happened was a single switch of the wedged hydrogen and the dashed OH to then be a wedged OH and a dashed hydrogen. And remember, when we did the double switch, we did it twice to invert stereochemistry and then recover it, right? In the whole process, doing something to make assigning R and S easier for ourselves. But if you can identify, especially in pairs, you know, in problems where you have to identify the relationship between molecules, if you can see a single switch has occurred, save that brain power. I didn't have to do anything here. I could have just said, oh, it's S over here, and I see just a single switch. That means it has to be R. The stereochemistry had to be inverted. Okay, that point aside, we see we have SS and RS. If this was RR, we would have enantiomers, but that's not the case. We have a configuration and then just a configuration that's not exactly opposite, but just different. And when you have that scenario, you have the relationship between your structures are what we call diastereomers. And yes, that is super hard to pronounce. You should feel very proud of yourself every time you say it correctly because it doesn't always come out the way you want it to. So diastereomers means, you know, you have one configuration and then you would just have a different configuration. It's not opposite, right? Because when it's opposite, you have enantiomers, okay? So these are a good old pair of diastereomers. On to the third problem. In the third problem, you'll see that we will have to do a double switch in each scenario. So what I did was I kind of broke out that double switch. I labeled this just as R. So you can go ahead and pause and look to see if you're confused on how this ended up being R and that ended up being S. You can just pause the video and look at this little analysis that I did. But if we take a look here, we have R here, R here, R here, and S there. So only a change from this stereocenter over here. So just like we had seen, it's not an exact opposite. We didn't end up with the same configuration because that can happen too, but we just have something different. So what's the relationship between these molecules? Well, they are diastereomers. Okay, so fourth one, let's do it. Okay, gang, so in the fourth problem, I was trying to bamboozle you. I was being a stinker. So if we take a look here, this, stereocenter, it's not a stereocenter, right? We're attached to 3 methyl groups here and here. So these structures are achiral. And because they're achiral, and we're structurally the same, right? So there's no stereocenter. Throw that out the window. And if we look at these structures, we have the same atom-to-atom connections. We have the exact same bonds. So there's no stereochemistry. Structurally, we're the same. So what's the relationship between these molecules? They're the same. They're identical. So this in problems where you have to figure out the relationship between molecules, sometimes someone will try to be clever and they will pretty much do a bunch of double switches. You could end up with the same stereochemistry from molecule to molecule. In that case, you have identical molecules. Or very quickly, if I showed you something like this, even this little bit of bonus content, these are CH3s. If someone asks you what the relationship here is, you might jump to say enantiomers because it looks like we've done a single switch. However, there's a plane of symmetry here. And when you have a plane of symmetry here, you're achiral. These are actually what we call mesostructures. So when you have symmetry, you're achiral. So then again, you can check the atom-to-atom connections. These will be identical structures as well. But I'm getting off track. In this scenario up here, we just don't have stereochemistry. Structurally, we're hooked up atom to atom the exact same way, so we are identical in this situation. So let's do this last one, finish problem 2, and then zoom through 3, call it a video. Okay, gang, so in the last problem of the second problem of this worksheet, if we take a look here, I will just stay out of the way, so if you want to pause the video, take a look at how the stereogenic configurations or stereo configurations ended up. Feel free to do that. But if you can see from ethyl on, we have S, R, R. And then over here, what I kind of did, if you want to think about it, was I flipped like a pancake and then I flopped over like that. So, it's important to note that this carbon that I'm asterisking is this one over here. The one I'm putting in a square is this one right here. And the one I'm going to put in a triangle is right here. Okay? So, if you take a look at each and every one, the asterisk here is an S, over here it's an R. The square here is an R, over here it's an S. And the triangle here is an R, and it's an S there. So at every stereocenter, if we go from back and forth, we can see that each stereocenter has an opposite configuration in the other structure. So because left hand to right hand, these are complete mirror images of one another. These are enantiomers. And it's important to know, if you're wondering, if I had something like SSR, right, not completely opposite of this would be a diastereomer, right, if I was going to go SSR going from left to right. So it's important to note that these are exactly opposite. That's why they're enantiomers. If there was anything else that wasn't complete opposite, then there would be some problems. But gang, of course, whatever. That was problem 2. Last one, problem 3. Let's finish this worksheet strong. Okay, gang, so in the last problem of this worksheet, we have 3 objectives. So in letter A, we look here. All we need to do is actually just draw the structure. So a little throwback to naming, except now we have a stereochemical twist. So I can see I'm drawing cyclohexane. So what I like to do is, when I have to draw a name that has stereochemistry, I just like to get the structural part down. I want to attach everybody to where they're supposed to be attached, and then I will go to the places where I need to do and reflect stereochemistry, and I'll make sure I have a wedge or a dash. So I have cyclohexane, and then on position 1, which I will draw up, we'll draw it over here because that's where I have it in the solution. I have an ethyl over here, so that's position 1. And then on 2 and 4, we have 2 chlorines. So chlorine here, that's 2, 3 and 4, chlorine down there. However, I need to reflect stereochemistry. So now that I have these marked properly, I have everyone attached. So structurally, I have this down, right? So now we just need to do the stereochemistry. So for the position 1, we have an S configuration, right? So these numbers correspond to these numbers. So 1, I need S. So what I like to do is just so we have our lowest priority group is a hydrogen here. I just need the answer to the question is this a wedge or a dash? And that will also answer the question over here. But let me just assign priority with how everyone's attached as of right now. I'll use black for this. So right here, I have a CH2 tie. Let me expand this. So CH2 and a CH2. But then over here, this is not a CH2. So you can see right off the bat, actually, put this ethyl back. This is priority 1, this is priority, this is priority 2, because we'll have a tie and then this will eventually win. This is priority 3, and let's just assume this is lowest priority. Let's assume this is facing away from us, assign it and see what we have. That means we would have R. If this was a wedge, oh boy, and then if this was a dash, however, this would give us R, we need this to be S. So the beauty of stereochemistry is we can just reverse this. We can have this be a dash, this could be a wedge. We don't have to draw that, but we could, and we could say that then this looks like R, but it's actually S. Okay? So we'll erase that. For chlorine, right, we need S and then we need R, so let's do this right here. Obviously chlorine is first priority. Then we see that this will win out in a tie at this position. This carbon is higher priority than this one. I'm going to erase this hydrogen here. It's a little messy. Then 3 over here. So assuming that this hydrogen is facing away from us, we would go in this direction, turn our wheel this way, S, and that's what we have at position 2. So what I'm going to do is I'm just going to turn this into a wedge. And that gives us the S configuration we need. And last but not least, this over here. Chlorine's obviously number 1. This branch wins up here. This is lower. So this would look like S, but we need R. So what I can do is it looks like it looks like S, but now it's actually R, because our lowest priority group, the undrawn hydrogen, would be facing towards us. This is our structure here in all of its glory. So now, moving to B. Draw an enantiomer and 2 diastereomers. So I'll use my colors for this. My enantiomer, yeah, I could verify R and S, but since I'm going to save my brain power, I will just flip. This will be a wedge, a dash, and a wedge, and the stereochemistry works itself out. So, right, because I'm just doing single switches of whatever this group is and hydrogen. This was an easy situation. So you can see I'm just flipping where all of these groups, just one switch, right? Because remember, all I'm doing is this. That inverts stereochemistry, right? So if I do that at every position, now I have the exact opposite. So you can take it to the bank that this is R, and this is S, okay? So now 2 diastereomers. So remember, this is everything that's just not the enantiomer and not the original structure. So what I'm going to go ahead and do, I am going to just flip once. So I will keep these chlorines the same, but I'm going to flip the ethyl. I'll make it a wedge. So then this would be R, S, and R, which is not the opposite of SSR. So then if I just need to do it one more time, I could, for example, let me make sure I do the same thing on the solutions, and of course I didn't. I'll draw all these combinations then. The one I just drew, and then the couple on the worksheet. Oh, I'm running out of space. If I only flipped this chlorine, then I would have S, R, and R. Again, not an enantiomer, not the original structure. And I'll do one more. I'll use up here. Needed more space. I could just flip, let me just make sure I'm doing, I could just flip this. That's the only one I haven't done the one flip with. I could make it a wedge. And then that would make this structure S, S, and S. Okay? So I gave you 3 diastereomers, and you only had to draw 2. So now, last but not least, and I really like this problem, we need to, so consider this following free radical halogenation, right? We're just going to picture X to be either, Cl2 or bromine. It doesn't matter. I am asking for all of the unique products that this can produce. And before stereochemistry, you would have just given me, a bunch of structures. You would have avoided duplicates. However, now stereochemistry matters. So what we can do is we could halogenate at this position, and this position, right? So, for example, let me redraw that. The unique positions here are square, triangle, and circle, right? Because these are the same and these are the same, right? The triangles, it doesn't matter if I put it here or here, they're the same, and it doesn't matter if I go circle or circle, because they're the same, right? It doesn't matter if I start on this end or that end. So, I just need to figure out, of these positions, where does stereochemistry occur, right? And, could I then have two structures for the price of one? So, first and foremost, I will just go ahead and do my circle structure. That's one. Now let me move to the triangle. Now, when I attach here, I have to ask myself, am I attached now to 4 different things? Because there's a hydrogen here. And the answer is yes. There's a CH3, here's a propyl, an H, and an X. So what I was looking for in this question is that at this position, you need to draw a wedge version as well as a dashed version. Okay? And now the big trick of this problem is, I feel like the big trip up will be, I'll give myself some more space for this, is that people will draw 2 structures for this. That, unfortunately, is not the case, because are we attached to 4 different things at this square position? The answer is no. We have 2 ethyl groups here. And in fact, right, so there's a plane of symmetry, 1, and there's 2 ethyl groups. So this is not a stereocenter. So there's no reason to draw a wedge or a dash. If you did draw 2 structures, wedge and dashed, they'd be the same. They would be duplicate structures, okay? Whew, gang, thank you for watching this video. If you're watching this video, that means you've thrown me some money and you supported jOeCHEM, and I cannot seriously thank you enough for that. Thank you for choosing jOeCHEM to help conquer, crush, annihilate carbon, get through OCHEM, hopefully with flying colors. I'm happy to be here now. I hope I'm rocking with you to the end. And no matter what, I hope to see you all in the next video.